Okay, so this is Statistical Rethinking, second edition, chapter 14. We're on question 14M5. I believe that this is the last of the medium difficult questions. Um, um, yeah, it seems to be. So, um, okay, so what are we going to do here? Okay, well, we're going to get to play with some Gaussian processes here. So we are supposed to modify the phylogenetic distance example to use group size as the outcome and brain size as the predictor. Okay, so assuming that brain size influences group size, what is your estimate of the effect? How does phylogeny influence the estimate? Okay, so if you remember from the chapter, what is going on here is that um, we are in the chapter we are trying to kind of flesh out a model where we believe that brain size is the outcome and it's predicted by group size. That somehow group size is affecting brain size. Okay. Now here we're going to reverse that, but that's fine. Now, one of the things that threatened to make this type of an analysis difficult is the fact that, of course, so we have to look across different species and look at their group sizes and their brain sizes. And one of the things that makes this difficult, of course, is that all of these different species are related to one extent or another, right? We're all related, uh, to one extent or another. And, I'm more closely related, to my mother than I am to a random person. But as long as that other thing is a person, I'm more closely related to them than I am to a chimpanzee. But I'm more closely related to a chimpanzee than I am a lemur, and I'm more related to a lemur than I am a lizard, and so on and so forth. Okay, so um, in other words, uh, there is this confound in the mix, which is just how similar these different species are that could be affecting both group size and brain size. Okay. Um, so uh, now in the mix, there was also the hypothesis that maybe body mass is affecting both of these. This is not really my area of expertise, and so I'm not really sure how brain size is or body mass is affecting group size and brain or group size anyway. Um, Makes sense. Maybe if you have mice, you can get 1,000 mice together, and they can feed on resources. But you can only have a few larger animals, and them still be able to utilize the same set of resources. So anyway, all right. So in order to account for that confound, which is just the relatedness of different species across a data set, we are going to employ a Gaussian process where we try to say that the more closely related two species are genetically, or maybe the right term is phylogenetically, then um, that should explain more of any associate, should explain some more of the association between group size and brain size. Okay. Now, and so we can think about this as trying to condition on the relatedness among groups, but because because there would be a value for every group with every other group, that just falls out into a matrix, and so the matrix is kind of the mathematical workhorse behind these Gaussian processes. Okay, so okay, so let's go through the example. Okay, so here I am just copying and pasting um, what was initially done in the book. Okay, and here we're just employing the basic model. So not really a Gaussian process. It kind of what we'll see is that it will look like a Gaussian process, but it's not really behaving like what we might think a Gaussian process is behaving like. Okay, but we just have our data. Here it is. Okay, so again, I'm just copying and pasting. So we have the log standard values for body size, brain size, group size, and then we also have this I matrix, IMAT. where I stands for identity, and that just means that it's a matrix of ones down the diagonal, zeros everywhere else. And we'll see what that does here in a second. Um, but this is the model that was used in the book. And this is us reversing the roles of brain size and group size, right? We're trying to find group size as a function of brain size, all right? So, so now in this mix, we are going to treat it as a Gaussian process, but this matrix that is representing the relationships between the species is just the IMAT matrix, the identity matrix. In other words, it's assuming that all of the species are independent, okay? That's what's happening here in this line. Now, why does it use, why is it using this? Why why put that in there at all if it's not really necessary? I think that the reason is because when we go to the next model, the Brownian motion model, all we're going to have to do, I'll come back up here in a second, is change the matrix that we're using. And in the next matrix, we'll just be using a different matrix called R. So in the next model, we'll use this matrix called R instead of the identity matrix, okay? All right. So, so I've already ran this. I'm not gonna, we're not gonna look at the output yet. We're gonna look at the very, very end. So now with the Brownian motion models, we need to install this package called ape. And then there's some commands here that the book doesn't really explain, and I didn't take too much time to understand, other than what we get, what we eventually get is a matrix that is representing the Brownian motion model, which basically says that that the more different two species are, the farther away they are. Okay. Yeah. Or how do I want to say this? The farther away they are phylogenetically, they are dissimilar in a linear fashion, right? So if you're 2 units dissimilar, then you're 2 units less. Okay. How do I want to say this? If you're 2 units further apart phylogenetically, then you're 2 units different. I think that's basically what's going on here. Okay. So we can kind of look at the first few rows of this matrix. Now this is a huge matrix, but we get the first few rows. It's just a correlation matrix, and we can visualize it. I think that the visualization is not great. The book suggests that we do this, but first of all, I think it's flipped, right? I think that this diagonal of dark spots should actually be going the other way, and well, anyway, it's not very easy to look at or derive much meaning from. So anyway, so now we run that model, okay? Again, it's the exact same model that we just saw, except now we have this R matrix, which is trying to represent the relationships phylogenetically among the different species. Okay, and now finally we come to the OU models, and this is much closer to what I think of when I think of a Gaussian process, right? Where, well, we'll see this in a second, but now we are making the presumed similarity between species, again, a function of their phylogenetic distance, but that relationship is no longer linear. And so to kind of show that, I want to plot that. So I have different eta values, okay, and different rho values, and then a bunch of possible distance values. D is the distance phylogenetically between species here. And so, so I just kind of run a little for loop here, and this is what we get. Okay, so roughly speaking, depending on what parameters you choose for eta and rho, but roughly speaking, what is happening here is that as you get more distant phylogenetically, your similarity is decreasing faster and faster and faster. Okay, so it's no longer linear, right? So as I go a little bit, as I go from 0 to 1, I have, or did I say faster and faster and faster? I meant slower and slower and slower, right? So a little distance causes a big decrease in similarity, but then if I go that same distance out here, the similarity is already very, very low, right? But it doesn't, doesn't accelerate very fast. Okay, So, so now we're going to run a model where, as part of the things that are being estimated, are these eta and rho parameters. Okay, as a way of trying to figure out, what is the relationship between phylogenetic distance and similarity. Uh, so, so we need to make a new matrix here, and we'll see how that plays out in a second. Again, we have the image. It's very, not easy to make a lot of sense out of it. So, okay. Okay, so here we have the model. Okay. And now this becomes the matrix that's kind of driving our Gaussian process. And there's a convenience function to make this particular, to encode this particular guy right here. But it's just the command COV underscore GPL1. And the book has a rethinking section where you can kind of learn how to make this by hand, but we have the convenience function here. So we run that, and now we're asked to look at what's happening with B. The brain size is a predictor of group size. So I'm going to plot the brain size coefficient for the three models here. Did I just flip those around? I think I may have. Yeah, there we go. Okay. So here in the first model, which was not really a proper Gaussian process, right, where all the species are treated as independently. I shouldn't say that it's not proper. It's just not the stereotypical Gaussian process. We see that brain size seems to be doing quite a bit of work, right? It's clear. It's far out here to the right. Okay. But now once we start to account for the phylogenetic similarities, we see that brain size is not doing a lot of prediction at all. Okay, so this should probably be expected, right? Because probably the phylogeny is doing quite a bit to explain some of the similarity between group size and brain size. And so once we account for it, we see that the apparent effect of brain size on group size is almost completely diminished, probably. So, all right, we'll call that good.